All right, this is lesson 18. It's from a cool down called, I'm looking it up right now, Printing Business. So, expressions can be written in different ways to highlight different aspects of a situation or to help us better understand what is happening. A growth rate tells us the percent change. As always, in percent change situations, it is important to know if the change is an increase or decrease. For example, a population is increasing by 20% each year. The growth rate is 20%. So after 1 year, 0.2 times the population at the beginning of that year is being added. If the initial population is P, the new population is P plus 0.2, which is 20% of the population. Or we could write it as 1 and then 0.2 more times P, or just 1.2p. So that's three different ways already that we can write this. Now, if a population is decreasing by 20% each year, the growth rate is negative 20%. So after 1 year, 0.2 times the population at the beginning of the year is being lost. So if the initial population is P, we could write it as P minus 0.2p. Or we could say we have 1 minus 0.2 times P, which is 0.8p. And this is something that we've talked about already. If your full population is 100%, growth of 20% would mean that you have 120% of your population the next year. If your population is decreasing 20% each year, well, if the full population is 100% and you lose 20%, you have 80% of your population left. Now, suppose the area A covered by a forest is currently 50 square miles and is growing by 2% each year, or 0.2%. 0.2% as the decimal is 0.002. If t represents time from now in years, we can express the area in two different ways. 1 for 100% of our area covered by a forest, plus 0.02% each year, or 1.002 to the t power for the number of years. So in this situation, the growth rate is 0.002, where the growth factor, what we're actually multiplying by to find the amount covered by forest the next year, is 1.002. Because 0.002 is such a small number, it may be difficult to tell from this function how quickly the forest is growing. We may find it more meaningful to measure the growth every decade or every century. Since there are 10 years in a decade, to find the growth rate in decades, we could take 1.002 to the 10th power, which approximately comes out to be 1.02. So this means it has a growth rate of about 2% per decade. So we could write it out like this, where we have the exact same thing that we had here, where t is in years, but we're starting off with a decade. So we're going to make it to the 10th power. This to the 10th power comes out to that, and this is our growth factor per decade. This is what we have to multiply 50 by for each decade to find the amount of area covered by forest. Now, if we measure the time in centuries, that's a little bit different. We would do the same thing, though. We would take this growth factor, the 1.002, and since we're looking at a century, we would take it to the 100th power. And then this right here becomes our growth factor per century. This is what we multiply the area of forest that we have now by for each century to find the amount of forest that we have later. So, cool down, printing business. A small printing company launched an online ordering system to expand its business. This equation represents the number of customers C has in terms of the number of months since it launched the ordering system. By what factor does the number of customers grow in 1 year? Well, how many months would be 1 year? And then what would our growth factor be? If y is time in years, write an equation for the number of customers as a function of the number of years. Well, you would just rewrite this using your new growth factor for each year. If the model continues to apply for a decade, by what factor will the number of customers grow in 1 decade? Well, how many months are in a decade? What would you have to multiply 400 by to figure out the number of customers? I hope this helps. Let me know if you have any questions.